String theory was supposed to be the theory of everything. Einstein's dream, a single equation that would unify quantum mechanics and general relativity. One framework to explain all of physics. Billions in funding, thousands of physicists, decades of work, and it failed. Not because the math doesn't work, but because even when it succeeds, it preserves the very distinction it was meant to eliminate. Today I'm going to show you why, and why that failure is actually evidence for something profound about the structure of reality itself. In the last video, I introduced you to the pattern. Reality exhibits pervasive explanatory twofoldness, irreducible complementary principles across physics, biology, consciousness, and theology. Today we're going deep on the hardest case, general relativity and quantum mechanics. If I can show you that even here, where unification has been the primary goal of theoretical physics for a century, the two-level structure is genuinely irreducible, then this pattern is real. So we're going to walk you through the explanatory indispensability tests applied to general relativity and quantum mechanics. So to just remind you of the test, for an instance to count as a load-bearing twofold, it must satisfy 5 criteria. Today we're applying this test rigorously to general relativity and quantum mechanics. If they pass, it means the distinction is genuinely irreducible, not a temporary gap in our knowledge, but a structural feature of reality. So we have distinctness, joint necessity, irreducibility, explanatory centrality, and empirical persistence. So for our first criteria, are they genuinely distinct? So general relativity is a geometric theory. It describes gravity as the curvature of space-time, mass and energy tell space-time how to curve, is deterministic and continuous. Quantum mechanics is a probabilistic theory. It describes reality at the smallest scales using wave functions. It's indeterministic and discrete. Energy comes in quantized chunks. These aren't just different equations, they're irreducible ontologies. One says space-time is smooth and deterministic. The other says it's fundamentally granular and probabilistic. They are therefore distinct. Our second criteria, do we need both? Can we explain everything with just general relativity? No. General relativity breaks down at quantum scales, inside black holes, at the Big Bang singularity, in particle accelerations. You need quantum mechanics. Can we explain everything with just quantum mechanics? No. Quantum mechanics requires a background space-time to operate in. The Schrödinger equation evolves in time. Time is part of space-time, which general relativity describes. Here's the killer. To build a GPS satellite, you need both. Quantum mechanics for the atomic clocks, general relativity for the gravitational time dilation. You can't build our most precise technology using only one framework. They are therefore jointly necessary. Our third criteria, can one be reduced to the other? So this is where things get interesting. Physicists have tried to reduce GR to QM, so general relativity, to quantum mechanics, and that's quantum gravity programs like quantum gravity. And they've also tried to reduce quantum mechanics to general relativity, so that's approaches like the Einstein-Podolsky-Rosen attempt. So every attempt either fails outright or succeeds only by preserving the distinction at a higher level. So we're going to have a look at 3 examples. So with string theory, we have strings as quantum objects. They vibrate in different modes. One mode corresponds to the graviton. That's the particle that mediates gravity. So this could appear to be a success with quantized gravity. Others not quite the case. The theory still requires a background spacetime for the strings to vibrate in. That background obeys Einstein's equations of general relativity. So you've got quantum strings vibrating in geometric space-time. So the twofold actually persists. With loop quantum gravity, this approach tries to quantize space-time itself. Space becomes a quantum network, discrete at the Planck scale. But matter fields are still described using standard quantum mechanics on the quantized geometry. The distinction between geometry, what general relativity is about, and what matter, what quantum mechanics describes, remains. So again, the twofold persists. So in our third example, we have anti-de Sitter / conformal field theory duality. So this is the most sophisticated attempt. It shows that a gravitational theory in a box space-time is mathematically equivalent to a quantum field theory on the boundary. But equivalence is not elimination. Both descriptions remain necessary for different calculations. The bulk / boundary structure is a twofold, just reframed. The pattern doesn't disappear, it transforms. Every attempt either fails outright or succeeds only by preserving the distinction at a higher level. So with string theory, quantum strings in geometric space-time. With quantum gravity, you have quantized geometry with matter fields. With the anti-de Sitter / conformal field theory duality, we have bulk / boundary duality. So the pattern doesn't disappear. It reappears in new forms, so therefore irreducible. For our fourth criteria, does the distinction do real work? So absolutely, the general relativity quantum mechanics distinction isn't decorative, it is load-bearing. So entire research programs depend on it. Cosmology needs general relativity for large-scale structure. Particle physics needs quantum mechanics for interactions. Black hole thermodynamics needs the interplay between both. And theoretical advances come from respecting the boundary, not erasing it. So Hawking radiation, for instance, emerges precisely at the interface between quantum field theory and curved spacetime. So they are, therefore, both explanatorily central. So our fifth criteria, empirical persistence. So has it survived theoretical revolutions? So general relativity was published in 1915, quantum mechanics in 1925. So since then, quantum field theory, the standard model, string theory, loop quantum gravity, ADS/CFT, every major theoretical development in physics for 100 years has encountered this structure and either failed to unify it or succeeded by preserving it in a new form. So this is not a temporary artifact, rather it is a deep structural feature. It's therefore empirically persistent. So general relativity and quantum mechanics pass all 5 criteria. They are distinct, jointly necessary, irreducible, explanatorily central, empirically persistent. They qualify as a genuine load-bearing twofold. This distinction is not provisional, not temporary, not waiting to be resolved. It's structural. So which relational logic do they exhibit? So they have asymmetric dependence, and here's why. Quantum mechanics presupposes a space-time background. The Schrödinger equation evolves in time. Time is part of the space-time manifold that general relativity describes. You can't do quantum mechanics without already having a notion of space-time geometry. But general relativity doesn't presuppose quantum mechanics in the same ways. You can write down Einstein's equations without reference to quantum theory. So classical general relativity is self-contained. So there's an ordering. General relativity provides the stage. Quantum mechanics describes what happens on that stage. So one is prior, the other presupposes it, and that's an instance of asymmetric dependence. And we find the same relational logic in a number of other instances. So with entropy and negentropy, global tendency is prior, local order presupposes it. With DNA code and epigenetic regulation, structural code is prior, regulation presupposes it. Again, past, future, you have temporal asymmetry. So we have the same logic in different domains with no causal connection between them. So what does this prove? It proves that even in the domain where unification has been the explicit goal for a century, and where we've had the smartest physicists with unlimited funding trying to eliminate the distinction, the twofold structure remains. Not because we're not smart enough, not because we don't have the right math yet, but because reality is structured this way. And if reality is structured this way here, in our most fundamental physics, and in biology, and in consciousness, and in several other independent domains, then we need to explain why. What kind of ultimate reality would generate this pattern? That's the question we'll answer in the next video.